In this project, we focused on three attacks. First is backside bus attack, and we chose multi-core processor system because in multi-core processor we share bus, cache, and DRAM is shared between all the cores, and that is vulnerable for denial of service attack. So first we chose backside bus attack, and we chose this configuration, and we ran all the simulation over CES simulator. So for that we chose a configuration which have 4 number of cores, and L1 cache size is 32 kilobyte, and L1 data cache size is also 32 kilobyte, and and L2 cache is shared, which is of having 2 MB size, and cache line is 64 byte. So and data TLB is of 120 entries, and instruction TLB is of 32 entries. So for backside bus attack, backside bus is used to access is used between L1 and L2, and whenever L1 mesh occurs, for accessing the L2 cache, backside bus is used. So in backside bus attack, we allocated memory in the application twice the size of L1 cache. We chose 32 kilobyte L1 cache, so we allocated 64 kilobyte memory, so that memory footprint is 64 kilobyte. For this we we wrote the code in assembly because we wanted to run it faster than the victim processes. So the code is accessing the cache lines, like this is accessing the starting of the array, starting address of the array, and next access is the 64 with the starting of the array. So it is going to access every time new cache line. So because it's accessing new cache line every time, it's going to be L1 cache miss. So by using this, we are generating L1 cache miss very fast. So at one point, backside bus will be saturated, and other victim processes will not be able to access L2 cache because it will not gain the access of backside bus. So yeah, and next is the front side bus attack. In front side, next is the L2 cache attack, in which we tried to sweep out the victim cache, victim process for memory footprint in L2 cache. So for that, as we chose 2 MB size of L2 cache, and we in this attack we allocated 2 MB size of memory footprint in attacker code. So attacker code will put request for memory very frequently, and it will access new cache line in each instruction. So it's a memory footprint of 2 MB, and L1 cache size memory is 32 KB. So after some time, it's going to saturate the backside bus, as well as it will sweep out the cache lines, the cache set used in L2 also, L2 cache. So it will sweep out the set used by the victim processes in the L2 cache. So L2 cache will experience, so victim processes will experience higher memory latency. So yeah, so only difference is that we are using memory footprint as 2 MB in in L2 cache attack. And yeah. In third type of attack is the front side bus attack, in which it's similar to backside bus attack and L2 cache attack, but we used 4 MB size of memory footprint in the application, so that it sweeps out all the L2 cache line used by the victim process in the L2 cache, and victim process will try to access the higher memory like DRAM, and victim process will experience higher memory latency. So yeah, these are the three type of attack we used. Yeah. Okay.
Okay, I explain about the result of our attacks. First, we do five kinds of attacks. Three of them is BSB, which is backside bus, and L2, which is L2 cache attack, and frontside bus attack that we mentioned before. And besides that, we do multiple attacks with one victim application. We do one victim application and two L2 attacks. And we do one victim application with two frontside bus attacks. So in this graph, there is 5 bars in each per each benchmark, and the leftmost bar is backside bus attack, and the second one is L2 cache, and third one is frontside bus. According to the paper we cited, backside bus attack is the most efficient attack among three is frontside bus attack, but in our results, this result shows that backside bus attack is the best, and then L2 cache attack is the next, and then frontside bus attack is the worst, has the worst efficient one. This bar is normalized IPC throwdown, which is 1 minus normalized IPC. So if the bar is higher, then that attack is more efficient, which means it throws down the victim application more. And we try to find out why backside bus attack is the best one. So we plot some more data. This is backside bus attack utilization, which is shown in per gigabyte per second. So backside bus, the maximum bandwidth is 64 gigabytes. So this shows that the backside bus attack and L2 and frontside bus attack consumes almost all bandwidth, or backside bus bandwidth. But you can show that there is a large amount of difference between backside bus attack and frontside bus attacks, which means that frontside bus is less efficient in consuming the backside bus. And this also, the next one is L2 cache miss. So the L2 cache miss should be higher in frontside bus attack, because frontside bus because in frontside bus attack, there will be a lot of cache misses to consume the frontside bus. But in L2 and backside bus, the cache miss is much less than frontside bus attack, because every data the attacker accesses fits into L2 cache. But in L2 cache attack, the attacker accesses all the lines in the L2 cache, so that the baseline it has a slightly higher cache misses than the baseline application. This is memory bus. As you can see, in frontside bus attack, the memory it consumes almost all memory bus, which is frontside bus, and the maximum bandwidth of frontside bus is 12.8 gigabyte, which is almost every. So frontside bus consumes almost every bandwidth, but L2 and backside bus doesn't consume that much of bandwidth. Well, the problem of L2 and frontside bus attack is, if you see this graph, this is L2 cache miss for the attacker. That in theoretically, the backside bus, all the attacks should have almost 100% L1 cache miss, because they access the data that is not in L1 cache. But in this graph, it shows that L2 cache miss and attack and frontside bus attack has much lower cache miss than the backside bus attack. And this is because the L2 cache miss attack and frontside burst attack has a lot, much bigger memory footprint than the backside burst attack. So in L2 cache miss attack, they access 2 megabyte memory footprint, and frontside burst attacks 4 megabyte memory footprint. And this is problematic because if you have a large memory footprint, you have much more TLB misses. So in this graph, you can see that backside burst attack, there's almost no TLB misses, and they don't spend any time in handling TLB misses. But in L2 cache misses, in L2 cache attack, you can see that they spend like almost 20% of time in handling TLB misses. And also in a frontside burst attack, you can see that it also spends like 13% of their time in handling TLB misses. This means that if you spend more time in handling TLB misses, the attack will be less efficient, because the rate of issuing load instruction is much slower than that when you don't have to handle the TLB misses. This is so the backside burst attack can issue more load instructions than these two attacks, and the backside burst attack has much higher efficiency than the rest two attacks. So we are trying to propose a better attack which is better than backside burst attack, and this is based on L2 cache miss attack, but we are trying to overcome the fact that L2 cache miss attack has a large footprint. By reducing the memory footprint, we can reduce the TLB misses, and we can also do backside burst attack, and also we can attack the L2 cache data in the victim's L2 cache data resides in L2 cache. So this is based on covert channel attack, and in covert channel attack, the attacker tried to detect what the victim thread access is. And our proposal is that we try to detect what the victim thread access is, and we try to access the data that maps to the same set with victim's data set. So if you see this graph, this is L2 cache access heat map from HMMER benchmark, and if you see this, the HMMER doesn't access all the sets in their lifetime. They access a particular set with very high access count. So if we attack these sets only, then we can have much lower, smaller memory footprint, and we can do better attack. So if we just access these sets rather than just sweeping whole L2 cache, then we can have much smaller memory footprint, and we can do backside burst attack and L2 cache miss attack with higher with better efficiency. And this is also from heat map from Soplex, and in this case we can do we can access just this range of sets. Then we can also be more efficient in issuing in our attack.